Hey, let's have a part 2 lesson on work and energy. So last time I had finished up by talking about the non-conservative forces of friction, air resistance, tension in a cord, rocket propulsion, because the action-reaction forces, you have a rocket going one way and you have the fuel spent going the other way, so of course you can't conserve those. And so these non-conservative forces aren't necessarily a bad thing, but they often can be, because it's just essentially energy is spent, and typically speaking you can't recover the energy that is put into that heat or that friction. Sometimes you can take up the energy in that heat, so a heat engine, the internal combustion engine, works off of a heat differential. One key thing to think about is it's not just about how much energy there is, but the difference in energy. So that comes up with entropy. Typically you'll teach entropy in chemistry. It is a concept in physics. We just let the chemists usually teach that until some higher end stuff, or AP2. But the idea being there that with more chaos, there is more randomness in the universe as time goes on. And so if I were to kind of split the room up, right, one side of the room is very hot and then the other side is very cold. So I haven't increased the energy, I just took some of the energy from here and put it here. And I've made this part of the room very hot, and I create some sort of division. And then I remove that division, that membrane, that barrier. There's going to be a flow of energy from where it's high energy, hot, to where it's low energy, to where it's cold. And in that process, maybe you can put a fan in between, because the air is flowing, the fan would spin and you can get some mechanical energy out of that. So the bottom line is, it's not always about having more energy, it's about the difference in energy levels between one position and the next, and how you capture the flow of energy. So with non-conservative forces, sometimes you can't always take advantage of that. So the work done by non-conservative forces is equal to the change in kinetic plus the change in potential. And so when you look at those changes, perhaps there's some amount of energy that is not accounted for, that is no longer there. That would be the heat produced by friction and things like that. So mechanical energy and its conservation. So the bottom line is that energy cannot be created nor destroyed, but it can only change forms. So when we look at this total mechanical energy of kinetic and potential energy, then it should be consistent, so long as we can assume that the friction is negligible and things like that. And so that's what we're going to do. Okay, so and that's the vast majority of our cases. We're going to look at cases where the friction is negligible and heat dissipation is negligible. If we want to, we can add that in, but usually unnecessary. So here we have the energy of a ball dropping, for example. So all of the potential energy is built up here. That's mgh, or mgy if you prefer. And as you let the rock or object drop, that energy is going to convert down to all kinetic. Somewhere in between, it'll be half and half. And you can simply determine the velocity of the object at any point in time by basically saying that the mgy that it had here is equal to the mgy plus 1/2 mv squared here. And so therefore you can determine its velocity at any point in time. And so we often will talk about it as buckets of energy. These sort of like, the bucket is going to be the same amount of stuff, energy, at all times. It's just a matter of what kind of stuff is in it. Is it kinetic or is it potential? But it's all the same energy. If we have a system where there is virtually no friction, or friction is negligible, something to consider is that all that matters is the height difference. So like the case of a roller coaster. And in fact, something that's very interesting about this is if I were to make a horizontal line here, let me in fact make this a nice red horizontal line. If I take this line, the roller coaster at any position, okay, let's say that this roller coaster was here, it would be moving at the same velocity here as it is here, because the potential energy is the same, therefore the kinetic energy should be the same. And so all that matters is the height change. If you want to, and this is where understanding how to manipulate problems is important, if you want to, you can make this position here to be 0 rather than ground level. It's unimportant to make ground level 0. If the height of this thing is 10 meters, then make your 10 meter mark the 0 meter mark. Make it work for you. The energy in an elastic spring is 1/2 kx squared. So the total energy of the system at any point in time, and in fact, for some reason they have not added in potential energy, even though he's clearly going up, so that's a mistake. But you could do that where his energy at any point in time would be 1/2 mv squared plus 1/2 kx squared plus mgy. That's what I would have done, is I would have added that in. But regardless, that total energy should be the same at any position throughout this event. There is nuclear energy, thermal energy, electrical energy, chemical energy. We will pretty much talk about some of those at another time, and some just get covered in other topics such as chemistry. Chemical energy we can talk about, but for the most part that'll be talked about in chemistry classes. Thermal energy, we'll just talk about it in a fairly generic sense, that is the energy caused by friction. If you want to go into that in more detail, we would typically cover that in AP Physics 2 with some thermodynamics. Of course, there's a blend between chemistry and physics there. Nuclear energy, we're not going to look too much into that, and we will look at electrical energy later in the year. So this is the topic that we will still talk more about. So work is done when energy is transferred from one object to another, or you can look at work being simply defined as the, if something has energy, has the ability to do work. That is a very simplistic definition, but works for most purposes. Okay, so energy cannot be created nor destroyed, it can just change forms. It's a little bit of a lie. Tiny bit. In truth, you can't create energy or matter combined. So you can convert between energy to matter or matter to energy, but the addition of the two together can't be created nor destroyed. That's where E equals mc squared comes into play, but for our purposes in this unit, we'll just say that energy cannot be created nor destroyed, because in order for it to be changed in that form, we'd have to look at nuclear energy considerations. So again, heat, so non-conservative forces, those will produce heat. That's the bottom line. So in fact, even the energy that's coming from the speakers that you're listening to right now, that energy is going throughout the room, and then it's dissipating, and it's literally heating up the walls. So if I were to make a loud sound and stop, you no longer hear that sound. Where did that energy go? The energy from that moment in time had gone onto the walls, and it had literally warmed up the walls in your room. What about your eardrums? Your eardrums had vibrated back and forth, and there was energy there, and then it dissipated and stopped. So the sound of my voice right now through those speakers is literally warming up your eardrums, and I'm warming your soul, is how I like to say it. Power. Power is work divided by time, and I will express that a little bit further here. So power being work divided by time, and remember that for work it is. In fact, let's look at units if we can here a little bit. So let's see if I can do a little bit of writing. So for work, right? Work is force times distance, and so the units here are going to be newtons, right, times meters. So Newton meters is in fact a unit, but we usually will talk about it in terms of joules. So for power, if power is equal to work divided by time, then we are looking at Newton meters divided by seconds, or joules per second. But another way to express that is with a different unit. And so we're going to express it as being, wait. So what's the unit for power? Watt? Yeah, right, exactly. So, watt's the unit for power, and that's the same thing as joules per second. So 1 watt is the same thing as 1 joule of energy being used up every second that goes by. Power is force times velocity. How? Well, what is distance divided by time? Okay, fundamentally, distance divided by time is velocity. So if you have a car that's having to overcome friction or a car that's going up a slope, the power that is required by to be put out by that engine is equal to the force times its velocity. Just to maintain its velocity, right? To maintain its velocity and overcome friction, overcome, the slope, whatever it might be, the power required is equal to the force times the velocity. So that's another way of looking at this. So that's our summary. So elastic potential energy is 1/2 kx squared. Gravitational potential energy is mgy, and kinetic energy is 1/2 mv squared. They will always express the work as being FD cosine theta, but I'm not so concerned about the cosine part. All that matters is that when you have a force that's being applied, but the motion of the object winds up being in this direction, figure out how much of the force is in the same direction as this displacement, multiply this force by this displacement, and personally I kind of ignore that part. Someone else might yell at me for saying it that way, but that is what it is. So power is the rate at which work is done, and that'll be expressed in a number of ways. If I can express one last thing, so there is an issue of pulleys, so or anything that creates what's known as a mechanical advantage. So instead of a pulley, let's create a more simplistic example of a lever. So a lever is put in a fulcrum, and over here you have some sort of mass, and then over on this side you have some sort of input force. So this mass is what's known as the load or the output force, and this is the input force. So you push down and this thing goes up. And so if the fulcrum was at the center, I have a feeling it's not going to really let me do this. Oh, yep, no, I didn't think so. So if what I can do is I can move the fulcrum, and let me erase it and draw a new one, then it'll let me move the fulcrum. So if I have the fulcrum at the dead center, then if you can imagine, this side will go down some distance, and this side will go up an equal distance on the other side if the fulcrum is at the center. So this is a mechanical advantage of what's known as 1. However, what if we were to shift this so that way the fulcrum is no longer at the center, but instead is shifted over here, where the load is very close to the fulcrum? In this case, the input force, you are going to push down a very long distance, and this thing is going to go up, relatively speaking, a small distance. So you are applying a force over this distance, and then you have an output force, and it's going to go this distance. The work in and the work out, are they different? Are you getting more work out than what you put in, or vice versa? And the answer to that is no. It's the same amount of work. The distance is increased, but your force input required decreases because most of the load is put onto the fulcrum. And so the force is amplified, but the trade-off is that you have to go farther. Okay, so yeah, I don't have to push as hard, but I have to go a longer distance to get the same output. So there's always some sort of trade-off between force and distance. So this is known as a mechanical advantage. So let's say that you have to move down a distance of 4 and this moves up a distance of 1. Then your ideal mechanical advantage would be a value of 4. So it's 4 times easier, theoretically, to push. So your force should be 4 times less than what you are getting out. So ideally, if there's no friction in the fulcrum than your mechanical advantage before. So that's called an ideal mechanical advantage. Your actual mechanical advantage is actually taking the ratio of the forces. It should be this output force divided by your input force. Now, maybe you are putting in a force of 1 Newton, and you're lifting a mass that is not 4 newtons, but maybe 3 newtons instead. So because of the friction, you are only able to lift a mass that is 3 newtons at its maximum, because there is some sort of friction here. So 3 divided by 1 would give you an actual mechanical advantage of 1, and so you do have some efficiency losses there. 3 divided by 4 would give you a 75% efficiency rating, which is not very good for a machine like this. Okay, so what is my key point here? It is that the work that you put in is equal to the work that you get out. At least it should be. At most, it would be equal. If anything, the work you put in is less than the work you get out because of the inefficiency of the system and the extra work is put into heat of the fulcrum itself. So what does that say about power? Does a machine like this increase your power? Well, no, because all that power is the work divided by time. So if your work is the same, right? I put in a certain amount of work, I get out the same amount of work, I'm pushing in the same amount of time that this is pushing out. So your power in pin is equal to the power that you get out. Those are the same powers. Okay, so work in is equal to the work out. Your power in is equal to the power out. Okay, so power, work divided by time. You can either increase the amount of work done in the same amount of time, or you can decrease the amount of time it takes to do that same work, and all of those things would increase your power output. Last thoughts is that yes, power is measured in watts. However, you can also express power in terms of horsepower. There is an actual conversion between the two. I want to say it's like 742 watts in 1 horsepower. Don't quote me on that, I'm probably wrong. But there is a direct conversion between the two. So just kind of think about that, and yeah, I think I'll leave it at that. So you guys have a good one, and let me know if you have questions. Take care.